derivatives and differentiation rules. These are essentially our shortcut rules to bypass doing the full definition of limits. We know from our tests and quizzes and assignments, limits are annoying. They take a really, really long time. So here are some helpful quote unquote shortcuts. We call these derivative rules. If your function is a constant, so for example, y equals 4, that is a constant function. What would it look like on a graph? What kind of a straight line? It's a horizontal straight line. What is the slope of a horizontal straight line? 0. So the derivative of a straight line should also be 0. And that's our first rule. I, of course, as a true mathematician, have to show you the full proof so that you are fully convinced that what I'm saying is true. So here is another notation, right? We remember f prime identifies a derivative, or d by dx. The derivative with respect to x of a function c should always be 0. So this is rule number 1. And the proof for that is if we take the limit as h goes to 0, and remember the limit is fx plus h minus f of x. Oh my, what happened here? There we go. All over h, right? Our function is just c minus c over h. This is going to be 0, right? Because we put x plus h in place of x. This function doesn't have an x, so I just have a constant. So c minus c is 0, therefore the derivative is 0. Simple? Great. Let's move on to rule number 2, the power rule. The power rule is when you have a function, essentially that's a polynomial, where you have some kind of a variable x that has an exponent n for pretty much any n. The derivative is identified by n times x, and now we reduce the power by 1, n minus 1. Okay, and let's do a really quick example here. Let's assume we have f of x. Oh, I guess I could do the general one. No, I'm going to do a specific example. F of x squared. So if I do the limit, h approaches 0, x plus h squared minus x squared all over h. And I use my trusty Pascal's triangle to figure out what are all my coefficients. All over h. The x squareds cancel. The h cancels from each term. And then I'll take the limit and make this go down to 0. I'm just left with 2x. There is a more formal proof that you can do this with any power of n. It does take a little bit longer to go through. I'm going to link a video to our playlist, but for today's purposes, I don't feel like we need to go into too much detail. Okay, so for example, try on your own if f of x equals x to the 22, or if f of x is x to the 5th plus 7, or if f of x is x cubed plus x minus 4, using what we just identified, the power rule and the constant rule. What would these derivatives be? F prime of x would equal what? 22 x to the power of 21. Okay, here f of x prime, 5x to the power 4, not plus 7. What is the derivative of a constant? It's 0. So the constant just goes away. We're all done with it. Okay, what about here? F of x prime, 3x squared plus 1. Good job. Right? Those are the derivatives. So we have a constant rule and we have a power rule. Those are the first two that we're going to talk about. Now remember back in unit 2, one second, back in unit 2 we talked about the limit laws, where if you have a polynomial, you can add up the individual limits. If you have a division, you can do the limit of the numerator, limit of the denominator, and then divide the results. These same limit rules apply to derivatives because limits are the definition of derivatives. Okay, so here in the second one, sorry, Gulshin, you had a question. Yes, it does. And we'll do an example of that in the next one. Yeah. Okay, example 1 asks you for two things. What is the derivative? And then evaluate it at the point -264. Okay, so my f of x is x to the power 6. So my f prime of x is what? 6x to the power 5. If I want to evaluate it at the point, means what is the derivative at that point? I say I am evaluating it at x equals 2, right? Because we're interested in the x values here. If I put in x equals 2, does anyone have a calculator? Or sorry, -2, my bad. I didn't see the negative there. -2. F prime evaluated at -2 is the same as 6 times -2 to the power 5. I'll give you a head start. It's a negative number. What would you get? 192. So this is the derivative at the point -2. Now, if I take this a step further and I ask you, what is the equation of the tangent line at this point? How would I write that now? You have a point. The derivative also represents the what in a line? The slope. Okay, so if I wanted to know what is the equation of the line, you have all the information you need. I just need you to dictate it to me. What would I write? -192, so that's my m, times bracket plus 2. Good. So this is point slope form, yeah? Plus 64. Okay, here's my point of interest. Here is the tangent at that point, or the slope, sorry, at that point. So the equation of the tangent is just mx plus b in point slope form. Okay, so this power rule applies to, as Gulsheed mentioned, any kind of power. It can be a fraction power, a negative power, whatever kind of power. As long as you understand how to minus a 1, you will be able to do this for anything. Okay, so now, for example, here, we're going to make, again, work smarter, not harder. I could do it in this way in fraction form. That seems like a pain in the butt. So I'm going to rewrite it as a different kind of exponent. How else could I write this? X to the power of -3. Okay, now I can see very easily what is f prime. So bring the exponent down, -3, x to the power of -4, right? N minus 1. -3 minus 1 is now -4. And you can leave it in this form, or you can write it as -3 over x to the power 4. Either way is fine. Okay, how do we write radicals? 1 over 2, right? So now I have a fraction as my exponent, but the rule still applies. When I go to take the derivative, f prime of x, what am I going to get now? Not quite. Oh, yes, sorry. Yes, you're right. -1 over 2, right? 1/2 minus 1 gives me a -1/2. How else can I write this? Square root x, where's the 2 go? Top or bottom? Bottom. So that's another way of writing it. Okay, so 1/2 is your coefficient to the power of -1/2. So negative means that the x is in the denominator. 1/2 means it's a radical. Okay, let's do a hands-on example here. Again, we want to work smarter, not harder. Is there a way I could rewrite this as a single exponent? Think of our exponent rules. I have x times x to the power of 1/2. Right, so this is x3/2, right? So what is now f prime of x? X to the 1/2, good, okay. And they have given us a specific point. So I want to evaluate this at x equals 1. So f prime evaluated at x equals 1 gives me (3/2). Okay, and again, what is the equation of the tangent line? So I'm looking for point slope form. What would I write? 3/2 is my m. X minus 1 plus 1. Okay, so point of interest and the slope at that point. All right. Rule number 3 is kind of a combo rule of what we've already talked about. If we have a function that is being multiplied by a constant, the constant can be pulled out of the equation if it's being multiplied. If it's being added or subtracted, the constant goes away. But if it's being multiplied, so for example, if we want the derivative of a constant times a function, then we can rewrite it constant on the outside, derivative function on the inside. So essentially, if we can factor out a 2 or a 4 or any other number, it stays on the outside. Just worry about the inside. Again, I'm going to attach a video for the proof just to keep things going because I feel like we're kind of getting the hang of it here. So here's again example 4. I have a function 8 times x cubed. Here's really the function, and here is a constant being multiplied. So this is 8 times f prime of x is what we could write the what we could do or what we want to do. So this will be 8 times, what is the derivative of just x cubed? 3x squared. So this simplifies to what? 24x squared, perfect. Okay, so it just multiplies the coefficient. Same thing here. I'm not going to rewrite it this time. Hopefully we can look at it and more or less do this in our heads. 6 times 8/3 times x to the power 5/3. And simplified, (16) x 5/3. Beautiful. Okay, so if we have a coefficient, the coefficient can just stay on the outside, and we can simplify as we go. In example 5, we have a bit of a word, not a word problem, but a bit more complex problem. We have a hyperbola with the equation xy equals 12, and we want to know at what points on this parabola is the tangent line parallel to this line here. Okay, couple of things going on. We want our final answer to be coordinates. At what points? We have an f of x here. We want the tangent line to be parallel. What does this word mean? Parallel lines have what in common? Yes, they have the same slope. So we want to have the same slope as this equation. What is the slope of that equation? Close. -3. This is y equals -3x. So we want our slope to be -3. If I wrote this in y equals form, what is my f of x? 12 over x. What's another way I can write this? I don't want denominators. 12x to the power -1. Okay, what is the derivative of this function? -12 x to the power -2, or we can say -12 over x squared. Okay, so I want to know at what point is this equal to this? So let's put them equal to each other. -12 over x squared equals -3. What am I doing? Walk me through it, quick. Quick. Okay, so my values are plus or minus 2, right? This will be true at 2 points. X equals plus or minus 2. So let's take a look at what are the full coordinates. If I put f of 2 and f of -2, this would give me 12. Oopsie, 12 over keep messing that up. 12 over 2, 12 over -2. So this is 6 and -6. So, final answer. At what points does this hyperbola have a tangent parallel to this line at the points 2, 6, -2, -6? Yes, sir. This is f prime. I'm looking for f. Where on the original function does the tangent line have the same slope? So we find the general slope equation. We equate it to -3 to find the exact x points. And we use the x points on the original equation to find the original coordinates. Okay, so step 1, find the general derivative. Step 2, make it equal to the parallel line you want. Step 3, find the x's that you need. And step 4, put it in the OG equation. Original. Have to keep up with your guys' lingo, right? All right, the sum and difference rule are exactly like the limits. Okay, if you have a function that has pluses and minuses in them, then you can do the individual pieces and then plus minus the derivatives. That's essentially what these two rules are. So this is technically rule number 3 and rule number 4. Okay, but we already did this with limits. So when you have a function that is separated by plus and minuses, you can treat them as two little pieces and add them, or 3 pieces, however pieces you have, and add and subtract them. So this is true for all things. So I can take the derivative of this, and the derivative of this, and then add them together. So 2 times x to the power 4, this gives me 4x. Oops, no it doesn't. 2 times 4 is 8. 8x cubed. And this one, this is the same thing as x to the 1/2. So this is 1 over 2 x to the negative 1/2. You can put them together if you like. You can factor out, what can we factor out? A 1 over 2 x to the 1/2. I'm just being picky here. 16 x to the, oh, I don't want to do this. Doesn't really make it look any cuter, so I'm just going to leave it there. You could rationalize it though. I don't want to do that either. Let's do the hard stuff tomorrow or on Monday. Okay, so if you have something separated by plus and minuses, just do them individually and add them together. G prime here, 4 times 6, 24, x to the power 3. 5 times 3 is 15, x to the power 2. 2, x to the power 0 is 1, and a constant gives me a 0, so the derivative here will reduce your degree. You should also remember that. The derivative of a polynomial will reduce the degree by 1. Just because of the power rule, right? We bring the exponent down, the exponent goes down by 1. So if you start with a quartic, you'll end up with a cubic. Poly will reduce degree by 1. Okay, let's take a look at this one here. Differentiate this. I don't want to. So what I'm going to do, again, smarter, not harder, I'm going to FOIL this out. This is a perfect square, right? This is x minus 2 root x times x minus 2 root x. This will give me x squared minus 2 times 2x over root x plus 4 over x. The first term squared, the last term squared, and the middle term is 2 times the product of A and B, right? The product of the first and second term. I want to, this one is the ugliest part, right? I want to rewrite that as one single x. So I'm going to try simplify here a little bit. This is x squared minus 4, 1 minus a half gives me a half. So that simplifies to that. Plus 4x to the minus 1. And now I can use the product rule, or sorry, the power rule. They're all plus and minus together, so I can just do the individual pieces. So f of x prime is 2x minus 2 over square root x minus 4. Right, so negative 4 times 1/2 minus 1 is how I got the middle term. Any questions on that one? I'm going to do our example 8 as our last example for today. We'll do the last page on Monday. So, yes, sir. What did I do wrong? Sorry, say that again. Ah, yes, thank you. I missed it. Over x squared. Thank you. Yes. Thank you. Thank you. Okay, example 8 is pretty much the same as example 5. So I want you to do those 4 steps together. Okay? Find the points. So your answer should be coordinates. On the curve, this is your original f of x, where the tangent line is horizontal. What does that mean? Slope is 0. Okay, so you are going to find f prime of x. You are going to find what makes f prime, oopsie, that's weird. What makes f prime of x 0? And then you're going to plug those values into the original function, and that should give you coordinates. You are going to decide how many coordinates that should give you. And I would leave the coordinates in exact form. They're not perfect numbers, but just leave them in exact form. Okay, so take a moment with your peers, sort that out.
What is it? I didn't get that updated. Days ago.
All right, answer is on the screen. As soon as you are ready, you can take a look and sort it out. Don't forget that when you are finding your roots, that when you take the square root of something, it should give you 2 answers, a positive and a negative.